Shut up and sit down.
Hey everybody, how's it going? Let me turn off that music again. Nice royalty music from Ben Sound. I'll put the link to it in show notes. Greetings to another fun session today. If you're watching, go ahead and give a shout out or ask questions, please. As usual, I start with a little bit of chit chat here and there. The weather has turned nice in Santa Cruz. We're having a very nice June. It was foggy, but now it's sunny. Today's tea, same flavor, I think. A little bit of China Gold tips with some decaf. I can't have much caffeine. I don't like who I become with a lot of caffeine. The mug today, while not being handmade by the famous Josh Burkus, aka Fuzzy Chef, which is links in the other show notes for that great kitty mug. Today, it's a birder mug. So there's all sorts of birds on it, which I love. My kids got this for me, I think, probably for Father's Day or my birthday or Hanukkah or something like that, just because I love birds and I drink a lot of tea. But it does bring up one complaint I have, which I have, quite strongly. Most of the birding paraphernalia in the world, like things that show off your pride, are East Coast birds. If you notice, most of these birds on here are East Coast birds. The two that give it away the most, that it should jump out at you right away, is the blue jay. Let me see if I can see the blue jay and the cardinal. Those are particularly East Coast. We do not get these here on the West Coast. I would like a mug with just West Coast birds on them. The struggle is real for me. Not at all. But I love this mug because it's got birds, and I like birds, and I love birding. I think that's all the chitter chatter I have today. Update on the reviewing of developer sites. I am going to say the last one went on too long. I did get good feedback from ESRI. They were very open to the suggestions I had, and I'm in dialogue with them about it. So kudos to you, ESRI, on that. And then I'm going to try to make it a little bit shorter, so I can't do really comprehensive reviews from a developer site unless someone really comes to me and says, hey, could you do a review? And then I might do a long one, which is actually just a videotaping of my interactions, and you're welcome to join me while I do it. But if it's just me doing it, I'll try to keep it short, and I'll try to put some bullet slides at the beginning and the end to say, here's some of the stuff that we're going to see, and then here's some of the stuff that we saw, right? Just so that you can see the main points I want to make about those sites. Because you could go all day with that kind of stuff. So, I think that's it. I think we're just going to jump into explain, analyze. So, for those of you who don't know, explain, analyze is what you can put into the SQL prompt, either through the interactive prompt or pgadmin when you're working with Postgres, and it'll show you what the query planner, if you just do explain, it'll show you what the query planner was planning to do when it took your SQL and turned it into an execution plan. And if you put in analyze after that, so if you do explain, analyze, it'll actually show you not only what it was planning to do, but what it actually did. And so this comes up a lot. I'd seen it a little bit before I started working at Crunchy. But then I really realized the power of it, especially as I started following the email, because anytime someone gets on and says, my query was slow, can you help me? Hey, my query's not working the way I want. The immediate reaction from everybody on the mailing list or in the PostgreSQL Slack channel or on IRC is going to be, what does explain analyze say? Right. So I'm doing this for you today. So you can do it for yourself. Do it even before you ask the question. And so then when you go to ask the question, you could be one of those good question askers where you can say, hey, my query's slow. I ran explain analyze. Here's my output. Here's the query I'm trying to run. Here's the output. And here's my /d of the table so you can see what indexes and stuff I have. All right. So let's go ahead and do it for today. Let's switch over to my desktop view and I'll make me smaller. So that's this one. All right. And we're going to be, again, working with learn.crunchydata.com. This is a free 24/7. Come here anytime you want, and you can go ahead and use Postgres. You can use any of these classes whenever you want. And today we're going to use the ones that are in PostgreSQL for application developers. Again, learn www.crunchydata.com, and we're going to start a course, and we're going to go to PostgreSQL Basic for Developers. Right? And then in here, you'll see there's a using, explain, analyze on your queries. So if I go too fast or you want to try some of this stuff yourself, come back here anytime you want and do this class. And I'll put a link again to this in the show notes. All right, so I already explained what explain analyze kind of does. The query planner, if you don't know what the query planner is, it's the part underneath. It's actually, some would argue, for end users, this is one of the most important parts of Postgres. Well, there's all the other, it's not the most important part, I shouldn't say that, but it's a very important part for us. It takes the SQL that we write and it says, okay, I'm going to come up with the optimum query plan given the SQL that you've written and the structure of your data underneath. And the reason it needs to come up with an optimal is because there's many ways that you can analyze data to get to the same result set. And so it's trying to find the one that's going to be the quickest, right? Which usually ends up meaning the least amount of page reads, but that's not always what it means. But so it's going to try to make an optimum, and it's going to do that by making a query tree. And so a lot of what we're going to be seeing today is query trees, not in the very beginning because our queries are so simple. But as we move to more, you'll see there's a query tree, and this is its best guess given the size of the data, the speed of your disks. Now, just as a quick background, and I don't explain this in the class, that last statement I said, the speed of your disks, that's actually a setting in PostgreSQL.conf, right? Where you can say how fast is it to do, or what's the cost of doing a read from disk, right? And so you might want to actually tweak that. I don't think the default settings I think expect spinny disks. I'm actually pretty positive it expects spinny disks. So it has a higher cost for random access from disk than if you had like an NVMe, right? So if you're doing a lot of querying and you should actually probably tune to the type of disks you have in your PostgreSQL.conf so the query planner can make better guesses about what things cost, right? So we're going to go through now and start. So let's clear this screen. That's just all the setup stuff. The first query we're going to do, we're using storm event data. You've seen me use this before, right? We're going to do some query on the storm event data. It's storms that happened in the United States, I think in the year 2018. I forget which government agency collects this data, so it's all open source. It's in our demo data sets from Crunchy Data. I'll give you a link to that in the show notes as well, if I remember. And we're just going to do a simple query, right? We're going to start really simple, and then we'll build up from there. So the first query is select star from SE details, limit 5. And we're only going to pick 5 because there's 60,000 rows. No point in seeing them all. And so we do a query, and that's what our data looks like, right? It's got a bunch of columns, and there's a bunch of storms in there. Now, for you, if it says more here, if you've not used the pSQL interactive prompt before, if it says more and you want to read more, you press space. If you don't want to see any more, you just press Q and you're out. All right. Now, let's do explain. So this is just the explain. It's not actually going to run the query. It's just going to say, here's what I would have done had I run the query, right? And so there's our output. And so you get this query plan. All right, so I'm going to break down the pieces like we do here. The first part, this whole line is a node. We only have one node in our entire tree because it's a very simple query. This node is going to run a sequence scan, or a sequential scan. Sorry, it's going to run a sequential scan, not a sequence scan, a sequential scan. Another name for this is a full table scan, right? And this just means it's going to go through the disk and read the whole table, right? Record by record, right? And it's going to run it on the SE detail table. The cost part here, now these cost numbers are arbitrary cost units. I have to read this because I have to remember. By default, 1 is the unit cost. 1 unit is the cost to fetch 1 disk page during a sequential scan. Right. So that's basic, and that's kind of why you see, since we're doing a sequential scan, you're kind of seeing these numbers be somewhat similar between the number of rows and the final cost that it thinks it's going to do to execute all this. This is the number of rows it's expecting to return. Note that that's just its estimate. If we had done a limit 5 in here, we can do a limit 5 in there. It's still going to say the same number, right? It still thinks it's going to come back with that many rows, but notice that now we've got 2 nodes in our tree. I didn't expect that. I haven't done this before. That's what I get for doing it on the fly. Note, this is how many it would do on the sequential scan. If there's a limit in there, you can see here it's going to actually only return 5 because it knows it's only going to return 5. Let's go back to the original. Sorry about that detail there. Let's say, so the rows is how many rows it thinks it's going to return. And in this case, it thinks it's going to return all of them. And then width is the width in number of bytes it thinks it's going to return a row. So each row will be 700, I think it's 715 bytes. Or is it K? No, 715 bytes to return that row. Note that sometimes there's a slight difference between what I have here in the text versus what's in here because our data sets change sometime and I don't want to have to change the notes all the time. But there might be slight differences, but it should be all this. It's the same ideas. The numbers just might be off a little. One other thing I want to say about rows is based, and this will come up again later, rows is based off of table statistics that PostgreSQL gathers when it does like a vacuum or a vacuum analyze. So if you do for the query planner to work properly, if you're going to actually that's why you want to actually do update vacuums and vacuum analyzes or analyzes if you do a lot of inserts and deletes, because that helps the query planner have better estimates of what's actually in the table and ranges of values so it can figure out what it's going to do. Right? So those table statistics are actually quite important for the query planner to do good queries. All right. One other thing you should know about these costs is they are not comparable between queries. So you can't do like an explain select star from SE details and explain select star from SE fatalities, and one has a higher cost than another in the explain analyze part. The explain part. Those doesn't mean this one will be slower or faster. They're not comparable between queries. That's a big bold marks in lots of different places where I read up on the topic. So obviously people must make this mistake a lot. So please do not think that you can use these cost estimates to compare between queries. All right. You want to see us change the width size? Let's do that. So if we go back to our original one, so we'll select this, right? Just a cleaner output. If we do select just the episode ID, right? Episode ID. You'll notice everything else stays the same because it still has to go through the same number of rows, but the width is now changed because we're just returning one 4-byte. It's probably an integer, right? We're just returning a 4-byte integer. So that's just how you can play around with the width of what's coming back. All right. That's it for that. Let's go on to the next one. Let's clear the screen again. Now we're going to do explain analyze. There's a huge caution here, and I'm going to bring this up twice. It's actually twice in the description because it is such a huge caution. I really think that developers misrepresented what analyze means. It should have been explain execute rather than explain analyze, right? It's the reason why I say that is when you put the analyze in there, it actually executes this next part of the statement. And you're like, oh, well, what's the big deal? Why do you care so much about that word? The reason I care so much about that word is for select statements, which don't actually change data, that's not a big problem. I don't care if you execute the statement. But if I have an insert or a delete, if I run explain analyze, it's actually going to run that insert or delete. So what that means is you'll actually delete by trying to figure out your query. You'll actually be deleting data or inserting data into your table. We'll see later how to handle that. Usually you just put that in a transaction, that question you want to analyze in a transaction and roll it back after you're done. But that's why I would love it to be explain execute. They're never going to change it now, but it should have been explain execute because that's a clearer idea about what's about to happen. It's not just that it's analyzing, it's actually executing your SQL statement. All right. Remember that. Because if you mess up your data, I don't want to get a lawsuit. Just saying. All right. So let's do an explain analyze on our statement that we did before. Right? And so everything in the beginning, we're doing a sequential scan on SE details, the cost, all that stays the same. The new stuff is here. So I didn't say what the original cost estimate is. The original cost estimate is how long it'll take to start up, right? How long it'll take to start up the query. And now we're starting to get some actual times. So we can see there is a little bit of actual time for this stuff to get started up, right? That's for the query to get started up. This is the actual time in milliseconds it took to execute the query, right? 26.953. That's the actual time in milliseconds it took to execute the query. Well, I shouldn't say execute. It's the time it took for this node. That's actually a misstatement. Rewind that. You never saw this. If this was Men in Black, wait, here's the Men in Black pen. Okay. The actual time here at the end is how long it took until this node to execute, right? This is just, again, everything on this line is related to this node. So this total time here is the total time it took for this node to execute. Here's how many rows it actually returned, which is good, so that the estimate and the actual lines up. So that's good. That means our statistics are good. And here's how many loops this node did. And so since this is a very simple query, we're not going to do any loops. Like there's a possibility for a node to have to process the data multiple times and do loops. This case, we do not have any. So this number here for total time is actually how long a single loop took to execute, for this node to execute. Okay. So in this case, since we have one node and there's no loops, then this is the total time it took for this node to execute. Planning time is how long it took for the query planner to figure out its query. Execution time is the total time it took between when we hit the enter button and when it was ready to start giving results back, right? And so why this is a bit different, why this is a bit longer than the total time it took for our nodes to execute is because there's the execution setup and shutdown. And that's usually what that difference in timing indicates, right? So this will always be a little bit longer than what it is here, but it shouldn't be much. It's here, so you can see it's an extra 3 milliseconds to set it up and tear it down, the executor. All right? And if you have questions, again, please ask them in the chat. Or if you're watching this at a later time, please put them in the YouTube comments and I'll come back and try to answer them. Okay? All right. So now we've covered explain, analyze. And we've covered all the basic statistics that come out for a single node. Let's get things a little bit more exciting. Oh, I'm going to show you how to protect because it's so important. So here's how we protect, right? So the first thing we're going to do is we're going to copy and paste. We're going to select. We're going to do a select. Alt, edit, paste. Right? So there's 55,667 rows in SE details, right? And here we're going to we're going to start by making a transaction, right? So if you don't know what a transaction is, it's basically a block that when you begin it, you can do all sorts of SQL statements inside. And then you, at the end of all those SQL statements, when you're done, you can either say commit, which means now actually do all those statements in the database. Or at the end, you can say roll back, which means don't do any of that stuff I just said, which is great because if you have like 6 steps and you throw an error on the 4th step, you can say, whoa, I don't want those first steps to be applied because they were all part of a chain that has to happen together. So roll all that back. So here we're going to say, okay, begin. Now I'm just going to copy and paste this one because I don't want to type all that. You don't like watching me put in typos. And we put that in. And so we're going to say explain analyze. So analyze means execute. Insert into my details table some made up stuff, right? And so there it gives you all the statistics we saw before. It says here's the insert, like here's the execution stuff, here's the results, the actual time and all that things, the planning time, all that. You get all that great stuff. But now what I'm going to do is I'm going to actually type roll back, and it's not case sensitive, so I'm not going to make it caps. So now I've rolled back. So if I actually do that select again, count, you'll see it's still the exact same number. So we didn't insert a new row, but we got the results we wanted. So that's how you actually protect your data from explain analyze in the cases of inserts, updates, and deletes, right? If you want to analyze any of them. Okay. Let's go on to step 3. So now let's do something a bit more exciting. I mean, all we've done so far is very simple select statements, and those aren't really that helpful. I'm going to start with the most common use case, where people come up with this all the time. Let's clear the screen again. Is we're going to select now where the state is where I grew up from, where I grew up in. So we're going to select just the event ID from SE details where the state equals New York. I grew up in New York State. So these are all the storms that happened in New York State, and you can see what the query planner did. So all this stuff is the same again at the top row, right? But now we're estimating that we're only going to bring back 1,700 rows or 1,700 rows. There's the estimate and there's the actual. Those are still relatively close, so thumbs up on that. We've added this new thing which says filter. And so this is actually how you're going to filter the data. It says where state is equal to New York and then text, right? So what the query planner actually did was cast this string that we passed in to a PostgreSQL data type, right? This doesn't actually make, is this a varchar? Is this a what? So it actually goes ahead and casts it to a text here to make it explicit that New York is actually a text data type, and we're going to use that in this filter. And then it tells you how many rows were removed by the filter. So it goes through and it says this is how many rows were actually removed by the filter. So this is good to tell you, okay, how selective, you thought your query was being really selective. Is it or is it not? And here in this case, it is, because came back with 1,700, let's say 1,500 or whatever. And we've got 53,000. So yeah, we actually got less than 10% of the rows coming back, right? Yes. No? Yeah. 10%. Yeah. Because 10% would be 5,000, right? So we're actually well under 10%. We're actually even we're under 5%. When we get the execution time and the planning time. So that's a nice selective query. That's good. But you're like, okay, 22.866 milliseconds. Whoa. Why is this taking so long? It's not actually really that long, but I want to pretend it's taking long. In other people's cases, it'll say this, you did a sequential scan on the whole table where you had a filter. You would expect, if it's too long, you want some way that it doesn't have to go scan the entire table to find the rows it wants. So the typical answer to this is, oh, you have an index. You should have an index. You should put an index on that. Or you have an index, but you put it on the wrong thing because it's not getting used. Let's see what it looks like when we actually do an index on state, right? So we're on what our filter condition is. So let's create an index here. So we're going to create index SE detail state index on SE detail state, right? So this is just a normal B tree index, standard, nothing complicated or new and exciting there. And then now when we explain analyze, we get something different. All right, we actually now get an interesting tree as opposed to the trees we got before. And we reduced our query time almost in half, right, by adding that index. And so let's walk through this tree. So the way the tree works is the top node of the tree is this bitmap heap scan. And then there's a recheck condition. And then there's a bitmap index scan as the bottom tree. This is going to get executed first. And then it's going to do the upper one. So the lower nodes in the tree always get executed first. And then it does the upper one. And so you're saying, wait a second, why didn't it just use the index straight up and just do an index scan? Well, what this one did, what a bitmap index scan does, is it looked at an index scan. The query planner probably looked at an index scan and said, actually, it's faster to do this. We're bringing back enough rows, 1,500 or 700, sorry, that what we're going to do is we're going to first go through the index and find all the matches in the index, build a bitmap of that, and then from that bitmap, go pull, and then you'll see we do a bitmap heap scan, right? So this is more like, this is very close to it's like a sequential scan on disk, but using the bitmap to do it. So it's going to go through in order on disk, picking out actually the ones that match. If we did just a straight index scan, it would find New York in the index, then go do a random access somewhere in the data to get that New York. And then maybe over here to get another New York. And then over here to get another New York. And then over here to get another New York, right? And it would be jumping around doing random access. What happens because of this one is it's actually go through the index, pull all the locations. Now we can go through the data matches in sequential order, right? Or close to sequential order. So we're not doing random access, we're doing sequential access. And sequential access is faster, right? So this isn't one of those examples where there's multiple paths. We could have done just a straight index scan, but there's been multiple paths to the same answer. And the query planner says, well, based on your disk and all the other things I know about this table, I think it's faster to do first just go through the index by itself, build a bitmap index, and then go through use that bitmap structure to pull from disk. I don't know if you wanted all that detail, but that's what it did. So it took 0.4 milliseconds to build the bitmap index, and then it then goes through that and takes another 12 milliseconds to go through and do all the pull back just the rows we needed, right? And it's doing a recheck on those conditions, right? So that's so it does this first, and then it does this, and that's how this works. And each of these actual times, this is the actual time for the whole node. So this one actually includes the time that's below down here as well, right? So if you wanted to get the time for just this node, you need to subtract this off this total time off this, if that makes sense. And we'll see how that, we'll see a nicer analysis of that in the final exercise. So I hope that makes sense. If you're watching and you have a question, again, please ask. What else should we say on this one? There's some stuff in the tutorial that talks about other reasons why a bitmap heap scan may be more efficient than an index scan. All right. Let's look at a join query now. So this is actually going to get even more a little bit more complicated explain analyze output. So what we're doing now is we're combining our events table, so the storm events, with fatalities. Some storms have fatalities. That's in a different table. So we're pulling back some different information from both of them. And we're joining where the event ID is the same in the details and the fatalities table. And the state equals New York. So this one was a fun one for me to try to figure out what was going on. And I went back and forth a bunch with some like Stephen Frost and some other people inside Crunchy on what's actually going on here. So again, it's hierarchical. There's two. And it's doing a nested loop. So now we're actually going to get some looping structures in here, which is fun. So to do a join, you have to have a bunch of join keys to start. And so what the query planner decided is first it's going to have a sequential scan on SA fatalities, right? We're doing a join on event ID. So we're going to just pull back all the event IDs in the fatality table. You're just going to get them all, right? Sequence scan. So we're doing a sequential scan on the fatalities. We're going to pull back all the event IDs. Nothing exciting there. There's going to be 613 rows, and that's just one loop. Go bloop. But what's happening in parallel, so this is not a parallel query, but happening at the same time, each time it reads off of disk a new event ID, it can feed it into this index scan on the detailed tables, right? Because the event ID is the primary key for the details table. So it's doing a primary key search. So it's index scanning on the primary key on the details table. So each time one of those indexes comes off of the fatalities table, it gets fed into into this node here, which then goes and pulls the actual data that matches, and then checks to see if it's in New York. Right? So it's a two-step process on this one. Actually, it's two-step process on just the index scan node. It first pulls the index based on the ID, right? This ID, go to the index, find it, great. Pull that record. Does the state match New York? If so, then return it, right? So basically, and the rows removed by filter is, it's good. Oh, and it's going to do this 613 times because there's 613 rows coming back, right? And so for each time it runs this, it may remove that row because there may not be a fatality in New York, right? And so there's actually only 14 fatalities in New York in this database due to storms. So this nested loop sends up this looping structure here. It does the sequential scan and then loops through each item of this and goes and does an index scan on each one individually. See how it's getting one row coming in, that's going to end one row coming out, and it's going to actually just say yes or no. And it runs 613 times. So if you wanted how long this node, this index scan node actually runs, You multiply 613 times the 0.005, and that will give you how long it took to execute this. Because remember, this actual time is per loop. So this would be 613 turns that. You add that to that, and you get to about 3 milliseconds total to run this whole query. Right? So 3.6 in total. So I hope that made sense in describing it. What I it's not a parallel query though. So parallel queries are something different. What it's just pointing out is the query executor doesn't actually have to wait on this whole thing to finish before it actually passes data into here. It would have to wait for this to finish if we put an order by or something which required this to be sorted or something to be happen on the entire data set before it could be passed on, right? But we didn't do that, and so it can just use this nested loop and just go, and then they all get done together, right? And the bigger picture, if we step away from explain analyze for a second, is why if you can, you should get your database to do your data operations for you rather than trying to do them in your code, because this is way smarter than anything I could have come up with and looped it. And it's right next to the data, right? It's right where the data is, rather than me pulling back the fatalities table, pulling back the events table, doing a dictionary or a hash map or whatever you want to call it in your language, getting the keys, only pulling the keys from this one. I wouldn't even like writing that. I know I could kind of write that in parallel or do streams or something, but it would take me forever. And here I just write one simple query and it all happens, right? So this is why you should learn SQL. Another good reason why you should learn SQL. Okay, so that's done with this exciting one. Let's move on to the final one of Explain Analyze. There's a nice little web tool. So if you find this a little bit too hard to read, I hope you find it easier to read now and a better sense of what's going on. I mean, I don't expect you an expert, but now you're like, oh, I get at least what these numbers mean, and that each row, each one of these big groupings is a node in a tree, and then things happen per node. Like, I kind of starting to understand it. I can see when an index is being used. I can see the total time my query took. That's a good way for me to get timing on it. But if you want a nice graphical tool or a nice way to share with other people, there's this explain.dpez.com. It's a Polish, I think he's Polish. I'm not exactly sure. I shouldn't say 100% he's Polish, but I'm pretty sure he's Polish. PostgreSQL developer. He's had this site up, I don't know. I think I just saw recently that it's been up for 15 years, maybe 10 years. I don't know. It's been up for a very long time. He runs it totally for free for the community. And we're going to click the link and it comes up here, right? So what it is a nice interactive tool for looking at the output of your query plan. So you can take this, and if you're not in Firefox, if you're in Chrome, you can just control copy. But if you're in Firefox, you have to say alt explain copy, because yay the web. And then we can paste that in, and you can give it a title, streaming fun query, right? And I want this plan to be visible on the history page. This just means whether other people, like the world, can see it if they want to or not. And this one, I want this plan to be obfuscated before saving. If you have column names that might be reveal what you're doing with your data set, and you don't want people to know, but you want other people, like you want to post, let's say you work with sensitive data, you don't want to but you don't want anybody to know what kind of data you're working on, and the names actually reveal it. You could do this, and you could do this, right? You don't want it to be visible. You do want this to obfuscate the names of the variables. So like state, well, I'll show you what happens to state, right? No, let's do it without, and then we'll do it the next time we'll do it with, because we're doing two queries. Let's do this without, and let's do this with this visible on the history page. So you put this in, and you say submit, and it goes through, and it makes this nice, what some people, and I actually consider it, a nice, more graphical output of your analysis. And so this link right here up at top, that actually is a URL you can share with other people. That's the unique identifier for a certain amount of time. I don't know how long, of your query. And you can share that with people, and they can come and look at your explain analyze. They can see this nice view. They can see the source right? But they can also see some nice stats, like what percentage of the time was spent in each of the nodes, right? All that kind of fun stuff. So it turns like in that one that we just did, the index scan is actually the longest thing. The nested loop itself is not that long. It's just the sequential scan of getting all the IDs. And the sequential scan is not. It's the index scan. Sorry, I take it back. The sequential scan of getting back all our IDs was really quick. The 615 rows, just read it right off disk in a row. It was the index scan of going through and looking for the going through the index, finding the event ID that matches, and then checking if it's New York or not. Right. Anyway, so back to the HTML. It includes something nice, which is the exclusive versus inclusive time. Exclusive time is how long this node took by itself, right? As opposed to what's reported in the explain analyze results, which shows the inclusive time, which is the entire time that node took. This says this is how long this part of the node took. So you remember this was the top node, the nested loop. You can see that's actually quite quick, and that most of that 3.6 milliseconds is spent doing the index scan here. And it's only it's half a millisecond to actually run the loop time at the end to assemble the results. You can see, so this rows number, rows X, tells you the difference between what the planner thought and what the actual number was, like when it was doing its estimates. And so you want these numbers to be around 1, relatively around 1. If it's lower or higher, that just means the query planner, well, in this case, it doesn't really count because it's just doing the index scan for the individual rows. But for this one, if this was like 7 or 8 or 0.2 or 0.3, that means your planner doesn't really have very accurate statistics, and maybe your query is not running well because your statistics are off, and you should maybe run analyze and run it more often. Right, and this tells you how many rows it returns and the number of loops. And so that's what it does. This is a new one. I've never seen this one before, so let's do this live. Let's see, add optimization. Optimization. Oh, interesting. So I think what this is if someone doesn't optimize, I think, what I'm guessing, I've never seen this one before, you can paste in what you think the person should have done. Because it didn't come up with a new thing in there automatically. It's just allowing someone to reply, right, to that query plan. That's fun. I like that. You can create an account there and do all sorts of stuff. He's got a pretty good help page that explains what's going on in here. I found it very helpful. If you don't ever want anyone else to see this, like you just were doing this for your own edification, you can delete this plan by using this link, right? And the plan's deleted and it's not available anywhere and no one can do anything. So let's look at we're going to make a new plan now. We're going to do a much more complicated one, which is this one, which is actually doing, it's this one. Here we're doing some groupings and some averaging, right? We're doing average age and count of fatalities in the U.S. states I've lived in for more than 2 weeks, sorted by average age. Right, so this is doing actually a lot more. The query planner has to do a lot more. And if we paste this in here and we submit, oops, actually, that's not what it wants. Good, thank you. Let me copy this and run it. Right, so we get this really big tree, right? Because we've got stuff like group bys and averaging, and because I'm putting order in, it has to wait until that's done before it can, right? So it's doing a bunch more. These are their sorts outside, and also just while we're copying and pasting, remember this is what actually usually ends up killing your speed because the query planner can't really do much with it because it's not relational algebra. So sorts are killers. There we go. So let's do this one. Now I don't want this one to be visible because I don't want to know anyone where I live, let's say, and I want this to be obfuscated. Like I don't want to know the variable names. I think it actually may even obfuscate some of the. Let's just see. Submit. Does a lot of obfuscation. So now if we go back and look at the source for this one, you'll notice, like it changes the index conditions. It changes the filter, right? It doesn't even show the names that I was looking for. The sort keys, everything's different. So it obfuscates all that stuff so that no one knows it can see it's inherently consistent, but anyone in the outside world has no idea that I had state names in here and which states I had, right? So it does a nice job of if you have sensitive data or something like that. So if you want to share it. And no one else can find it, right? It's not on the history page. So this is what, EM54. And so these are the most recent. Right? You won't find EM54 here. But if I wanted to, and you can see this I'll put it in the chat. If you come back sometime later, that should be there for a while, right? So that link, and if you look at that link, you'll get to see my query. And then it says all the execution time. It's really, I can't believe how quick that is. Now look at that. 3 milliseconds to do all that analysis. That's just amazing to me. And it's ordered and everything, group bys and averaging, and just amazing to me. Anyway, I love databases. So that's it. That's the end. There's a bunch of there's a blog series from Dipez. I don't know what his real name is, so I'll just call him Dipez. There's a explanatory on Doc from that side. A nice video introduction from Josh Burkus, aka Fuzzy Chef, aka Cat Mug Maker, and Stephen Frost's explaining use explain to identify and fix slow queries. So Josh's in there does some explaining and fixing, but his is mostly to introduce, explain, and the query planner. And Stephen's focuses a lot. He does some of that, but he also focuses a lot more on how do you fix when you see like it comes back with, the query's taking 30 seconds, 40 seconds. What do you do to fix that? And then the PostgreSQL Wiki has a good collection of explained resources as well. Okay. So with that, I'm going to wrap up the video. I will tell you that next week on Wednesday, I'm going to do the DevRel, review of a developer site or a documentation site from application developer's perspective. I'm going to do the Postgres site. Since I did Esri to start with, I thought I would pick one that is nearer to what I work with every day. So I'll talk about the PostgreSQL.org documentation from a developer's perspective, an application developer's perspective. And then I'm not sure what I'm going to do on Friday. I would love some feedback. I think for Friday, I might do some of the new stuff that Crunchy has come out with, which is PG Tile Serve and PG Feature Serve. Like I may give a quick introduction to those, or I may just do PG Feature Serve and have Martin Davis on the call with me. So let me know if that would be even of more interest to you so you can meet Martin. He works at Crunchy. He's Dr. JTS, the person who was one of the original authors of JTS, the Java Topology Suite, which is the basis of GEOS. Anyway, that's just some ideas. Other than that, I ain't got much right now for you. So I hope you have a great weekend. Again, leave questions and stuff in the comments, and I'll chat with you later. Have fun, everybody. Wait, hold on. I'll say bye once I do this, and I keep playing this, and I'll say bye. Okay, everybody. See ya.